Hi, and welcome to MSc. In today's lesson, we're going to be looking at another example of a chemical equilibria, this time one that involves determining equilibrium concentrations. So here's an example. Given the chemical reaction below, and again I've kept it generic, these could be any substances, determine the equilibrium concentrations of all substances if 2 moles of each substance was placed in a 1 liter vessel and the reaction was allowed to reach equilibrium at 300 degrees, or 300 Kelvin, pardon me. The equilibrium constant for this reaction is going to be 9.0. Okay, again, the 1 liter vessel allows us to easily calculate concentrations because concentration is moles per liter. So these will end up being concentrations of 2 moles per liter for each substance originally. When we deal with these types of problems, again, we want to set up our ICE chart, the initial, change, and equilibrium. So keep in mind that you always want to set up these charts. These ICE charts are really useful. And then we know from this that we had 2 moles per decimeter cubed of each of these originally present. The change in this, again, we're going to lose, I like to assume we always lose reactant and get product. If it went the other way, if the equilibrium lied more to the left, then you'd get a negative x and all your values would still work out just fine. The change here I'm going to assume is that A loses, and because of the stoichiometry there's a 2 up here, and so that's why there's a 2 down here. We're going to gain some of B and we're going to gain some of C. Our equilibrium concentrations then will be 2 minus 2x for A, 2 plus x for B, and 2 plus x for C. Unlike other examples where we already know the Kc value, and I did a video on that already, you might want to go check that video out if you have not done so already, is we have to figure out this value of x. I don't know any equilibrium concentrations to figure out the x value. And I do know my equilibrium constant value, my 9.0. So I do know, and I can keep in the back of my head, that Kc is 9. So let's look at what the actual equation is for Kc though. And again, it's always products raised to the exponent over reactants raised to their coefficient. And the coefficients become those exponents. So what we have here then, if I substitute in for B, it's going to be 2 plus x, and C is going to be 2 plus x, and the concentration of A at equilibrium will be 2 minus 2x, and that's all squared because of the stoichiometry of the problem. We also know now that Kc is 9, so you feel free to put in the 9 here if you'd like at this point as well. If it was maybe a decimal number, I might just leave it as Kc until near the end of this step. So this is where we have to do a little bit of rearranging. These types of problems could lead to a quadratic. It could lead to the quadratic formula. Most of the time, though, you'll find, especially at the high school level, that that's not what they're going to do. They're not looking to test that. They're looking to see if you can rearrange and solve. This one will involve some algebra, but will not involve the quadratic formula. And for the most part, most of the time IB questions and other advanced questions won't involve the quadratic formula because, again, that's not what they're trying to test. So let's work through this. In the numerator, you can notice I have the same term twice. So I could square it. And in the denominator, I have a squared term already. And so rather than expanding these and creating quadratics, what I can do here is I can take the square root of both sides. And if I do that, I get rid of the squareds and things become a lot nicer for me. So I get 3 is equal to 2 plus x over 2 minus 2x. Now I still have some algebra to do with this, certainly, but this is a lot nicer than it was going to be if I tried to expand these into quadratics and work with them that way. So opposite of dividing by 2 minus 2x is multiplying. So on the other side here, I'll write 3 times 2 minus 2x equals 2 plus x. Then I actually do want to expand and distribute this because I'm looking to isolate for x, right? That's my goal here, is to find out what x is. So this will give me 6 minus 6x equals 2 plus x. Now I can move the negative 6x across to the right, and I can move the 2 across to the left. So the 2 would become negative on this side, and the 6x would become positive on this side. This is 4. This is 7x. And then I will divide both sides by 7. And I'll get that x is equal to 4/7, which for rounding purposes I'll write out as a decimal. And that will be 0.571428, and this continues on. Okay, so that's my value of x. Now, going way back to this equation that we had way up here, I now need to use that to calculate my equilibrium values. So please don't forget that we're not done at this stage. We have more to do. So let's look here and say, okay, well, the concentration of A, we had said at equilibrium that the concentration of A was 2 minus 2x. So this is 2 minus 2 times my 0.57 value here. And if I do that, I get 0.857, and we'll round to 2 sig figs because that was what was provided in the question. This would be 0.86 mole per decimeter cubed, and again, I can write that as just a capital M for molarity if I want. My concentration of B is going to be equal to 2 plus x. So this will be 2 plus that 0.57. So 2.57, but again, we are keeping 2 sig figs only, so this will be 2.6 moles per decimeter cubed. The nice thing here is that this is also equal to my concentration of C, because again, way back here, we noticed that they will have the same amount at equilibrium. So we can just state that they are the same. And so we've calculated our equilibrium values. Notice we have more products than reactants at equilibrium, and that makes sense because our Kc value was 9. So it would make sense that the numerator in our Kc expression would be larger than our denominator, and we should have more of B and C than we do of A at equilibrium. I hope this brief example has been helpful. Thank you very much for watching, and thank you very much for listening.